So, integration by trigonometric substitution continued, and this time we have integrals that have definite limits. So, one thing you're going to face is if I use different variables to integrate, I have to change the limits of integration. But you could, kind of, if you're going to change back to the original variable at the end, then don't bother. Just call them by new names, and at the end, backtrack. What I mean is, while you're integrating using new variables, you're not evaluating because you're still integrating. Once you're done integrating and you've got these weird limits, you don't know what they are, then go back to the original variable x, and then you could use the original limits for evaluation. This looks nasty, doesn't it? The fifth power, I mean, it's scary. But that's suggestive of secant, tangent squared plus 1 equals secant squared, so that secant squared minus 1 is tangent squared. We just need to figure out with this 9, but that's not a big deal, because you just let, I could have let 3x equal secant squared. Sorry, 3x, I could originally have let, instead of letting it equal u, I could let 3x equal secant theta from the get-go, if I had enough experience, I guess, which I ended up doing anyway in the next substitution. So I'll do this slow, right? I want to put this in a more familiar form, so I'll let u equal 3x. That gives me a u squared minus 1, and then I'll see what's going on here. If u is 3x, then x to the 5th is u to the 5th over 3 to the 5th. Fine. Dx is du over 3. And then put in replace all the old variables with the u variables. I put a to b, but then because only 3, I figured out what they are just by multiplying by 3. Since the new variable is 3 times the old, just take 3 times that, you get square root of 2, and 3 times that, you get 2. Otherwise, if it wasn't that easy, I wouldn't have bothered at all. You guys see what I mean? Okay, that's starting to look like something more familiar. Sweeping out the constants. I call them alpha to beta, but I just figured 1, that's easy enough, right? Because now what I'm going to do is let u equal secant theta, because I have secant squared theta minus 1, which is, what's secant squared theta minus 1? Tangent squared. I need more of you guys to not be so shy. Tangent squared. And the square root of that breaks out the tangent. I cross my fingers with that u to the 5th. Okay, so u is secant theta, du is secant theta, tangent theta, d theta. I'm going to need that. Remember, these constants were swept to the outside. So there's my du. And my u to the 5th is secant to the 5th. It is what it is. And because this was secant squared minus 1, which is tangent squared, square root, there's my tangent theta from that. And sure enough, I get an immediate cancellation with the tangent theta that came from the du. And lo and behold, it looked really bad, but now I've reduced to cosine to the 4th. 1 over secant to the 4th is cosine to the 4th. And yeah, I need some new limits. But I'm lazy, so I'm just going to call them names and we'll continue. Well, how do we do cosine to the fourth? Now you draw on your scales from earlier sections. You write it as cosine squared times cosine squared, and then use the double angle, the half angle identity. This time it's the correct one. If you guys remember the fun we had last time. At the end, those are the correct ones. Okay, so I'm going to square that out first. I can do this one, no problem. I can do that one, no problem. Right? And that one I'll use the half angle formula for. We have an extra 1/4 that came out from here. Notice that the way the identity was used is cosine fourth theta. So cosine squared theta is 1 plus cosine 2 theta over 2. That's where that came from. It was cosine to the fourth, so that's why it's squared there. All right, expand it, and then I'll use the half angle formula again. The integral of 1 d theta is theta. And the integral of antiderivative of cosine 2 theta is sine 2 theta over 2. That's why that 2 is gone. And I just have that remain to deal with. But I put alpha beta. I haven't evaluated yet. I just want to handle the most technical issue first, and that's the integration. Okay, no big deal. Nice problem. I'm still waiting it out for the limits here, but I'm done the integration. Done with the integration. And then I use the half angle formula and cosine squared again. Cosine squared 2 theta is 1 plus cosine 4 theta over 2. And now I can integrate all of it. That gives me theta over 2. That theta over 2 joins that theta to make 3 over 2 theta. And then cosine 4 theta, the antiderivative is sine 4 theta over 4. There was 2 already, that's why the over 8. And it looks like I chose to figure out what the new limits of integration are. Got an interesting answer with lots of pi. That's a very tricky integral to do, isn't it? It looked really bad. But it worked out. See the skill you got now? You can handle problems that seemed intractable before. Now, if you want to trace back, as far as like the limits right here, would it have been easier for me to go back to the original variable? Not really, because how would I do it? Well, it's easy. You go back to the first place where you define theta, which was right here. And just remember that u was 3x. So along the way, when you look back at this, you'll see that I figured out the new limits of integration every time I change variables, which was done once, then 2 times. Okay? First u, which was trivial, and then theta. How did we get the pi over 4, for example? We started with square root of 2, so since u is secant theta, theta is secant inverse u, theta is secant inverse u, so secant inverse square root of 2 is like cosine inverse 1 over root 2, and we know what that is. That's pi over 4. Okay, and so on for the thetas. Questions? Short lectures are the best. I mean, if I could actually get this done, that would be great. All right.